Log on, tune in, find out. Another good idea from Cambridge.
Hodge polynomials for SL2C character varieties of genus 1 and 2.
Thank you, Hugo. First of all, thanks to the organizers for giving me this opportunity to fill this free spot that you got. and the object of the talk is to compute the Hodge-Deligne polynomial of character varieties for genus 1 and 2. And this is a paper that we just uploaded yesterday to the archive, and we got this funny number. Somebody told me that this is a lucky number in Catalonia. So we will see. So let me tell you what is the plan for the talk, and please don't get sleepy. So there will be an introduction where I will show you some known results on these polynomials, and then I will tell you what are the character varieties, SL2 character varieties that we were going to compute, because as I say in the abstract, there will be various character varieties, and we are going to compute the Deligne-Hodge polynomials. Let me say Hodge polynomials instead of Deligne-Hodge polynomials all the time. And then I will explain some basic properties of these polynomials, the main idea for these computations, and then some methods, and then the results and comparison with the well-known Poincare polynomials. So X will be a compact Riemann surface of genus G, and G, let's say a complex reductively group. So then the G character variety of X is the moduli of representations of the fundamental group of X into G. So the topology of G character varieties has been studied extensively over the past 10 years, with the main purpose of proving certain conjectures on the mirror symmetry phenomena exhibiting the non-abelian Hodge theory of the curve. So for complex linear groups, GLNC and SLNC, the representations can be understood as local systems, and then hence defining flat bundles of degree 0 over X. So if you want to move to different degrees, the G local systems corresponds to the representations of the fundamental group minus one fixed point, and with a fixed representation of the loop around the point, given the so-called twisted character varieties that Thomas Hausel explained on Monday. So the non-abelian Hodge theory for the curve tell us that there is a homeomorphism between the moduli spaces of representations, I mean the character varieties, the G character varieties, and the moduli spaces of G Higgs bundles. I'm not going to get into the Higgs bundles thing, but have been talked about during the workshop. Another direction is to consider more my points and then fix the conjugacy classes around of the loops, of the representations of the loops around the points. So then the corresponding character variety is what I call a parabolic character variety, which is this one. And then again, the non-abelian Hodge theory for the curve tell us that the moduli space of in this case parabolic Higgs bundles, which are Higgs bundles with a parabolic structure over the marked points, correspond to these parabolic character varieties. Parabolic Higgs bundles is another thing that we have been talking about, and it was explained by Alessia Mandini in her talk on Monday. So there are some known results already. So in the 87, in his seminal paper, Hitchin he introduced Higgs bundles, the notion of Higgs bundles, and also he already computed the Poincare polynomial for the SL2C Higgs bundles, which are Higgs bundles with fixed determinant. In 95, in his thesis, Peter Goten computed the Poincare polynomials for SL3C, And the Poincaré polynomials for the parabolic situation, is this one? I was using d for the degree, and d plus alpha will be the parabolic degree, which is the one corresponding for the parabolic situation. So there will be also a plus alpha. So Boda and Yokogawa computed for the rank 2 case and fixed determinant, and in the rank 3 case it was computed more recently in 2007 by García Prada, Goten, and Muñoz. What about then the Deligne-Hodge polynomials? Recently was uploaded to the archive a paper by García Prada, Heinloth, and Smith, where they extend the method given by Hitchin and Goten to the rank 4 case using motifs of the moduli space. Well, they compute the motif of the moduli space of Higgs bundles of rank 4. In the other side, Hausel and Rodriguez Villegas in 2008 give a formula for the Deligne-Hodge polynomials of the character varieties for GL and C. And Merev last summer following the work by Hausel and Rodriguez Villegas, gave the Deligne-Hodge polynomial for the SL and C character variety. So also the parabolic situation has been studied already by Hausel, Lettery, and Rodriguez Villegas in a preprint that I think it will come. But coming back to the first motivation, Hausel and Thaddeus in 2003 showed that the Strominger, Yau, and Zaslow mirror symmetry hold for the moduli space of Higgs bundles in the SL2C and SL3C cases, and then conjecture that there will be the same mirror symmetry stand for any G and G Langlands dual for G complex. So the question, another conjecture, is what happens with the character variety side. So why to question this thing? That's because these moduli spaces, let me write it here, the moduli space for Higgs bundles is homeomorphic to this moduli space of representations, but there is another moduli space, which is the moduli space of flat connections, which is even complex analytical to the moduli space of character varieties, and it is proved that the mixed Hodge structures of these two moduli spaces are the same, coincide. So it makes sense to ask if there is also a mirror symmetry conjecture for the character varieties. So what are the character varieties we are going to talk about? Our goal will be give another method. Hausel and Rodriguez Villegas method is an arithmetic method. Our will be a geometric one to compute the Deligne-Hodge polynomials for some other character varieties. Realize that here we are fixing some conjugacy class. So C will be the identity minus the identity, the Jordan forms, or the diagonal ones. So in this case, when we fix to be the minus identity, we get the twisted character varieties computed by Hausel, and we get, when we go for the diagonal case, it corresponds to the parabolic character varieties. So let me recall now some definitions, just to not get you lost. What I was talking about is the mixed Hodge structure, and then we first need to define what is a pure Hodge structure of weight k, and it consists on a finite dimensional complex vector space H with a real structure and a decomposition of it. The pure Hodge structure gives us a Hodge filtration, which is a descending filtration, where the graded pieces are the graded pieces are the H, P, K minus P pieces of the decomposition. Then a mixed Hodge structure is defined in a different way. It's also a finite dimensional complex vector space, but instead of saying what are the pieces, what we say is what we ask for is two filtrations, an ascending and a descending filtration, such that the descending filtration gives us a pure Hodge structure of weight k on each piece of the graded piece of the descending filtration. Sorry, of the ascending filtration. So we denote the Hodge numbers as the HPQ, which are these graded pieces. Well, the dimension of these graded pieces. So, well, when recall that for any quasi-projective algebraic variety, its cohomology, its K cohomology has mixed Hodge structure, and they are pure if the quasi-projective algebraic variety is also smooth and projective. This was proved by Deligne. So in these cases, the Hodge numbers are the ones for the Hodge for the cohomology of the variety. And then recall also that if the set is smooth and connected of dimension n, then you have this duality. So the Deligne-Hodge polynomial we are going to compute is the following one. It's given by this Euler characteristic, which is the alternate sum of the mixed Hodge numbers. When the numbers for p different than q are 0, then the Deligne-Hodge polynomial only depends on the product of u by v. Hence, we are going to denote it q, and we call these varieties of mixed type. So we will have this problem of pronunciation to say that we will have mixed Hodge structure of varieties of mixed type. So just forgive me. Also, recall that there is another polynomial, which is the mixed Hodge polynomial, which is giving you the all the Hodge numbers. This polynomial gives you an alternate sum, so then you don't get the Hodge numbers, the whole mixed Hodge numbers. So, okay, before continuing, let me just tell you some basic properties of these Deligne-Hodge polynomials. As we are using an Euler characteristic, they are you can prove that they have this additivity property for when you have your variety as a union, disjoint union of the varieties. Also, it is easy to prove because you know what is the cohomology of Cn and the projective space. It's easy to compute the Deligne-Hodge polynomials for Cn and Pn. But then there are three interesting things that will come now. That are they behave like multiplicative for some kind of fibrations. You have a fiber bundle with which is Zariski locally trivial, then it is multiplicative. If the fibration is with fibers projective spaces, it is also multiplicative. And even more if it is if you have a principal fiber bundle with G, a connected complexity group, it is also multiplicative. One can prove more. These three properties are summarized in this proposition, which is if you have a base connected, then an algebraic fiber bundle, which is not necessarily locally trivial in the Zariski topology, and such that the monodromy action is trivial on the cohomology of the fibers, then you can compute the Deligne-Hodge polynomial of Z as the multiplication of the Deligne-Hodge polynomial for the fiber and the base. So then, this thing about fibrations gives us the following idea. Just let's consider this map, the commutator. Okay, till then, this is a PGL equivariant map. So what if we just take, this is the Fm minus 1, the inverse of the minus identity. So then this is just the SL2C twisted character variety we were talking about. So then, okay, consider all the orbits in this space. Notice that all the orbits, the union of all the orbits, is a disjoint union, and it behaves well for the Deligne-Hodge polynomial. So it will give you the whole space above. So the sum, the sum of these pieces of the Hodge-Deligne polynomial for these pieces will give you the Deligne-Hodge polynomial for this space. So okay, let's compute the Deligne-Hodge polynomial for SL2C. Then this is easy. We just use the fibration thing that we just proved, and then this is a locally trivial fibration for SL2C, which sends the matrices A, B, C, D to AB. So then then it's easy to compute. What is the Deligne-Hodge polynomial of C2 minus 0? Well, the 1 by C2 minus the 1 point. So it's Q to the square minus 1. And which is the one for C? Q. Then that's the multiplication, and you get the E polynomial for SL2C. Okay. So which one will be the one for SL2C to something? This thing to this something. Okay, so the idea then will be decompose SL2C into its orbits to get pieces whose Deligne-Hodge polynomials are easy to compute. So let me now, instead of using, I will denote by the whole orbit the identity, and the whole orbit will be minus the identity, instead of writing C of, conjugate orbits of something. So if we add the Deligne-Hodge polynomials for the identity, the minus identity, the Jordan forms, and the diagonal ones, we will get the Hodge polynomial we just compute. This is a bigger, more complicated way of computing than the previous one, but will give us a clue of how to compute other ones, like the twisted character variety that we have before. So, okay, for the identity, easy. If you just do the conjugation, you just get 1 point. So the Hodge polynomial is just 1. The same for the minus identity, and then they come the Jordan forms. Then one can see that the Jordan forms, the stabilizer for the Jordan forms is C, and one can compute, just checking the matrices, that the Hodge polynomial of this one is just the product of these two ones, which gives you Q to the square minus 1. But then we get to the diagonal matrices, and then there is a problem because these diagonal matrices are of this form. You have lambda and lambda minus 1, but then you can act by Z2 and go for lambda minus 1 and lambda. So we need a method for what happens when you have an action of a Z2 action on your variety. So just a little example. Let's first denote by plus minus the Hodge polynomial with respect to the plus minus invariant parts for the set 2 action, and note that if we denote by a set the E of set by set 2, then the minus part is just the total minus this invariant part. So then, for instance, just as an example, let's take set equal to C star. Then with this action, one can see that there is an isomorphism from C star by set 2 to C, sending the 0 to the infinity. So then one sees that the plus part will be Q, which is this one, and the minus is just the rest. Minus 1 has to be. So then we prove the following proposition. Then you can do the following. I mean, if you have a diagram of vibrations where B is connected and P bar and P are smooth morphics, if you have this vibration, locally trivial vibration in the usual topology, and the monodromy action of P1 in the cohomology of the fibers is trivial, then the Hodge polynomial, the Deligne-Hodge polynomial for set acted by set 2 is of this form. The ingredients for the proof are just to describe the Leray spectral sequences for the two vibrations, and then also there is another ingredient that is saying that the spectral sequences respect the mixed Hodge structures, and then playing this way you get that this formula. Also that checking that with this assumption on the monodromy, the monodromy of this one factors through set 2 on the cohomology of the fibers here. So then let's go to our case, the diagonal matrices. So the stabilizer of them is C star. So we have this diamond, and then where the maps are the following. This is a covering of our diagonal matrices. So here we send lambda p to p times, so sorry, this should be C lambda. No, okay, now this is lambda p, and then here you, let me write it. So you just send this one to this. The one here is the trace, and here you send lambda to lambda plus lambda inverse. So this satisfies our proposition from before above. So if we write the fibers and the base, then EB plus is this one, is Q minus these 2 points, EB minus is the rest, minus 1. Then you can compute also the same for the fibers, and you get that the Deligne-Hodge polynomial for this orbit is Q to the third minus 2Q squared minus Q. Okay, let's plug all this together, and then you have 2 Q to the square minus 1 plus 2 times, and this one, so it has to give Q to the third minus Q, and it is okay. So we got a method on how to compute this thing. So now extend this to the genus 1 case. So we consider this map, and then we stratify SL2C to the square in the following way. Just x0 is the inverse image of over the identity, this is the inverse image over the minus identity, the Jordan forms, and the diagonal ones. Again, we can check the computations the same way as before. But then, just recall that then x0 by PGL2C will give you this variety etc. So what we can do is first compute the Hodge-Deligne polynomials for these pieces, and then check how is the quotient, and then compute the one for the quotient. So this gives us this result for genus 1. Observe that this is just 1 point, and that here already these Jordan forms are different. These are palindromic, as was explained by Thomas Hausel on Monday. And the result for genus 2 is the following. When you also have different Deligne-Hodge polynomials for the Jordan forms, this is a twisted character variety which agrees with Hausel computations, and it's also this also is also palindromic. This one is also palindromic, and this one is the one with the reducibles, so this is the singular one. So now we have computed the Deligne-Hodge polynomials, but we can say we know a lot about the topology then. Well, recall that there is this relation for the sorry, I forgot to put here the compact support. There's this relation with the Poincaré polynomial with compact support. But there is a problem. The information given by the Deligne-Hodge polynomial, as it has this Euler characteristic in the definition, it has the alternate sum, so it doesn't give us the whole Hodge numbers. So, but our computations during this explicit description of the stratifications again, and so give us the possibility to give the Hodge, the mixed Hodge numbers here. So we can compute the Poincaré polynomials, and for instance, I was just giving some ones that are not in the literature, and also in the case of the Jordan minus, I mean the -1, -1, and 1 in the off diagonal, the explicit description can give us the Betti numbers, but this is not enough to get the Hodge numbers. You can do a kind of Sudoku to see what can be the alternate sums which give you the same Betti numbers. So these are the possibilities that you can find, for instance, for the Hodge numbers for these Betti numbers. And so I will stop here.
Any questions?
Just a small one. So this last result that you present is for rank 2, right?
Yes. Everything is for rank 2 because it's SL2C.
Yeah. Do you think, I mean, can you generalize it to the case N?
Well, as you saw,
what is the difficulty? This is the question.
I was explaining you here. For instance, you have the set 2 action on this. If you have bigger matrices, you will have set n action or more things. So, I mean.
Any more questions? Okay, let's thank Marina once more.